Our speaker of today will be Taya Hamilton. So Taya is the clinical consultant for Fourier Intelligence. She was previously the clinical manager at Bionics Lab and has substantial research experience in MIT and Berkeley Neurological Institute. Taya is currently based in Boston, and because of the time difference, it's 3 o'clock in the morning right now, so she can't physically join the session today. So this session is actually pre-recorded, but all of your questions will be answered by our clinical application manager, Sarah Lim. The topic of today is bringing arm recovery within reach. So please welcome Taya.
It is my absolute pleasure to be presenting to you this evening on a topic that I'm both very passionate about and invested in exploring over the course of my career. My name is Taya Hamilton. I am a clinical neurotechnology and rehabilitation research consultant with a background working in stroke rehabilitation as a physiotherapist. During part 1 of Fourier's exciting neurorehabilitation webinar series, I will be focusing on bringing arm recovery within reach, and in particular how neurorehabilitation robots can be used to achieve better outcomes for patients recovering from neurological injury or disease such as stroke. Before I begin, I'd like to disclose my current affiliations consulting with Fourier Intelligence and my research positions within this field with Dr. David Lin at Massachusetts General Hospital and with Dr. Hermano Ego Krebs at MIT. So let's start by outlining the problem. Every year, 15 million people suffer a stroke globally, with 2/3 of this population experiencing residual impairment. Despite significant medical advances in acute management over the last 20 years, stroke continues to be a leading cause of chronic disability and health-related costs in the United States and across the globe. There are now more people living with chronic stroke-related disability. Upper extremity hemiparesis is the most common impairment, with the prevalence as high as 80% in the acute and 40% in the chronic phase post-stroke. Consequently, 4 out of 5 patients leave inpatient rehabilitation with limited arm function. So why does this matter? It's not just an economic health burden, it matters to our patients. Patients need and want more arm recovery than what conventional therapy has been able to offer. In a study by Lai and colleagues, patients deemed recovered with a score of 95 or more on the Barthel Index reported ongoing dissatisfaction with their upper limb impairment and long-lasting, costly restrictions to the participation in activities of daily living and their quality of life. It also is a problem that doesn't go away easily or quickly, with 50% of people continuing to have motor impairment beyond 4 years. I can almost pinpoint the moment in time when I made the decision to focus on arm recovery in my subsequent research and consulting roles. I was a very experienced stroke physician that asked me one day during a stroke unit multidisciplinary meeting, "What is it about the arm? You seem to get patients up and moving and walking, but recovery of the arm still seems to be subsidiary in comparison." I think this is a frustration that's not only felt by patients, but also by us as clinicians, and one that us as a field we should be continuing to strive to optimize with advances both in research and in intelligent technology development. So what is arm recovery and what should it look like? Well, true arm recovery encompasses both motor control and strength components, and not compensation. Recovery in the therapeutic setting is aiming to minimize compensation and really optimize the restitution of both motor control and strength. Clinical outcome measures, unfortunately, really do not differentiate or capture in any way true arm recovery from compensation in their gross measurement and observation of movement patterns. Another area of consideration that's not often discussed is the influence of non-motor components on arm recovery. What is the impact of impairments such as cognition, memory, perception, and vision, and how should these impairments be addressed in the choice of the intervention that we use for arm recovery? Another important distinction related to arm recovery in therapy is the concept of motor control compared to strength. It may be asked, well, why should rehab focus on targeting motor control? Well, the answer is very eloquently stated by Dr. John Krakow and his colleagues. The motor control and not strength is essential to use the upper extremity in everyday complex tasks, tasks such as typing, writing, and cooking, and it may determine how much the arm is used during activities of daily living. Some literature shows that improvements in motor control may be limited to just the first 5 weeks post-stroke, particularly in patients with mild to moderate arm impairment. More likely, ongoing improvements are happened for those patients with more severe impairments. Some speculate that improvements are largely mediated by strength in both the subacute and chronic stages. So it must be noted that strength training and learning compensatory strategies can really happen at any time, whereas as a field, we should be focusing on what interventions can really augment spontaneous biological recovery in the early phases after stroke and really focus on the motor control component. So what are these interventions that can be used to optimize arm recovery after stroke? According to evidence-based guidelines and systematic reviews, the following interventions have been shown to provide improvements in arm function. But of course, the evidence for a lot of these interventions is still lacking or requires further validation. Of relevance to the discussion about improving arm recovery and the components of motor control and strength, robotics really provides a unique opportunity to maximize and optimize the intensity and quality of therapy received, and minimize the emergence of compensatory patterns in arm movement. It also provides additional benefit of offering goal-specific motor control retraining tasks, as well as appropriate strength training, such that patients can be addressed in the continuum of care and with a wide range of functional levels within the one platform. And for these reasons, I'll now focus on how neurorehabilitation robots can be used to promote arm recovery following stroke and other neurological injuries or disease. So upper extremity robots come in many different forms and for different purposes. The robots you see pictured here are just a sample of robots currently commercially available. The ones you see here are the Armeo Power, where the patient's arm must be measured and fit to the robotic device. Or there's the assistive purposes in the home. This one here is Myomo's Myo Pro, where the patient uses the robot to assist with activities of daily living. Another joint-specific exoskeleton is Fourier's handy rehab device. There are also many end-effector robots on the market, such as Fourier's Arm Motors M2 Pro or Wrist Motors devices, the InMotion Arm, the Rio Go, or the Tyromotion Diego or Amadeo devices. These end effectors may have a quicker setup time and often work multiple joints at once. Robotics has been studied and shown to be safe and effective for a really wide range of patient populations, acute, subacute, and chronic, in both adults and to a lesser extent in children, in stroke, cerebral palsy, incomplete spinal cord injury, Parkinson's disease, multiple sclerosis, and to a lesser extent, neurodegenerative conditions and acquired brain injury. And I think it's really because of the heterogeneity of ABI and neurodegenerative conditions that we haven't seen more evidence in these patient populations. The technology really does target patients with more moderate to severe impairments, such as those where their participation in independent or even manually assisted rehabilitation is really limited. So we have far more therapy options, far less therapy options available to these patients. But the good thing about robots is that the therapy can be adapted to be more challenging, such that it's also appropriate for patients with milder impairments by simply changing the level of therapy or the position in which their therapy is provided. There are many advantages and real key features of implementing neurorehabilitation robotics, which address the needs of achieving arm recovery, which we'll now explore in more detail, one by one. Firstly, the design of neurorehabilitation robots is really optimal for standardizing patient setup and both evaluation and therapy purposes. This allows a really more reproducible assessment and therapy. Robotic systems often have the ability to control the degree of freedom during a task or movement, and therefore reducing the risk of retraining compensatory movements. And you can see that in the picture displayed here. For planar or two-dimensional robotic systems, Therapy can be isolated to retraining motor control instead of strength, as there's often a gravity eliminated position and support for the forearm. As a result of this setup and the support provided for the affected arm, the clinician now has their hands free and their attention free to focus on providing feedback and facilitate more proximal shoulder or trunk movements, which further reduces the risk of retraining compensatory movements and ensures the patients really engage in the task and receiving individualized therapy. The interface and nature of robotic therapy also allows a challenge of the task to be appropriately graded for the individual based on their objective assessment of the patient's performance. And that's why we can really consider robotics as a platform for the continuum of care. It addresses the needs both of those patients in the early stages, focusing on motor control, and then has the ability really to be graded for strength requirements in the later stages of recovery in subacute or chronic. Determining the outcomes of therapy interventions and patient progress in rehabilitation is often limited by subjectivity and insensitivity of clinical outcome measures. Robot-derived kinematics can provide a standardized and objective measure of a patient's motor control and movement quality, and it does correlate with well-known clinical measures, as many studies have shown to date. And these can include the Fugl-Meyer motor power scales or basically manual muscle testing scales, among others. The metrics provided in a robotic evaluation report often include measures of peak and mean velocity, deviation or movement aim, accuracy, smoothness, range of motion, mean and peak force or patient effort, many of which that you can see in this example report from Fourier's Arm-Modus M2 Pro. The sensitivity of these metrics, as you can imagine, has the potential to not only enhance our understanding of stroke recovery, but also our patients' motivation and engagement in their results and progress in therapy. Patients get tired and frustrated with hearing the same feedback verbally from their therapists, such as, "Good job, great work, that looks much better." They don't really feel a sense of ownership of their therapy, whereas patients can feel empowered by seeing their numbers change over time in these reports and begin to own their therapy and own their progress and lead to greater motivation to continue working hard towards recovery. Advances in robotic technology such as Fourier's Rehab Hub concept now allow connectivity and networking capability to be able to provide group therapy with multiple devices. And you can see an example of that pictured here in the Rehab Hub concept. Robotic group therapy has the potential to provide more therapy using less staff in order to enhance the efficiency of therapy in clinical environments. And although more research is definitely required to validate this model, studies to date have shown that even when treating patients with severe impairments post-stroke, a ratio of 1 clinician to 3 patients is both safe and feasible. I think this is a really exciting area for us to continue to research and explore. A maybe obvious advantage of robots is the potential for providing motivating, interactive, and engaging tasks through the visual interface. Evidence shows that brain plasticity and the potential for greater recovery is enhanced when training is challenging and varied, accompanied by feedback, motivating and goal-orientated, and interesting. You can see all of these elements are incorporated into one of our patient's favorite activities on the Arm-Modus M2 called Whack-A-Mole. You can see that there's the ability to challenge the patient more with the range of motion and the resistance provided, as well as real-time feedback of the patient's performance. You can see that the task can be both motivating and goal-orientated, and definitely they report that it's interesting. Other studies have also shown that rehabilitation outcomes and impairment reduction is related to the degree of the patient's engagement. Therefore, it's a really key factor to consider when we're planning and executing the therapy for our patients in this field. Another key feature of robotic therapy is the higher intensity and greater number of movement repetitions able to be achieved in a therapy session. It's really unclear in the literature the exact dosage of therapy required to induce meaningful changes, but we know we need a lot. Animal studies indicate that between 600 repetitions for adults and 400 repetitions for children are required to induce neuroplasticity. Observational studies of conventional therapy indicate that we are far from achieving adequate intensity in the clinical environment to induce changes following neurological injury or disease. Some report just a mean of 32 repetitions per session of arm therapy, or 16 minutes of occupational or physical therapy per day. You can see that we're falling far from what the research is showing that is needed. Robotic therapy programs are often designed to achieve hundreds, if not thousands, of repetitions per session that may be tailored to the individual. And as a result, robotics can be considered a comprehensive tool for clinicians to provide evidence-based practice. A key feature for the effectiveness of therapy is also the longevity of the desired outcome. Robotics has been shown to produce lasting improvements in motor control, up to 3 years after ceasing therapy, even in the chronic stroke population. In addition, improvements in shoulder pain have also been shown to be sustained 4 months after therapy, just showing us that robotics is not only for pure motor and can be considered effective or applicable to other conditions such as shoulder pain, which is really a key influencer in arm recovery following stroke. Another opportunity that robotics offers is the option of providing comprehensive multidisciplinary rehabilitation. Arm recovery really is influenced by other non-motor components of neurological disease or injury. And it makes sense that robotics for rehabilitation should also include therapy modes focusing on cognition, attention, memory, problem solving, neglect, speech. And this is an area that hasn't typically been seen in the robots currently available, and I think will be an emerging area that we're currently seeing in both research and in the commercial robots that are now in the clinical setting. I thought I'd share with you now an example of a comprehensive neurorehabilitation robot that incorporates all of the key features that we've discussed so far of the advantages of robotics in stroke rehabilitation.
Our Modus M2 Pro is the new generation upper extremity rehabilitation robot from Furrier Intelligence. Featuring a user-friendly interface, it can be operated within 1 minute, making it easier to use. Our Modus enables assessment covering range of motion, muscle strength, and cognitive ability. Based on assessment results, it recommends training parameters and completes training related to motor control, cognition, ADL, etc. Since our Modus offers scores of movement trails, therapists can customize training programs accordingly. Through intelligent assistance adjustments, our Modus guides users to establish correct movement patterns in the early stage. Late-stage rehabilitation needs can also be met by changing the resistance. With a new generation MMU, our Modus simulates different levels of resistive force, inertia, elastic force, and obstacles, creating an interactive training environment. Built-in sensors measure every movement with accuracy. Each training session ends with a report that provides a statistical reference for therapy. Our Modus optimizes neurorehabilitation outcomes via a more efficient training method. It also replaces tedious manual training with fun and highly interactive exercises.
As you can see, the Our Modus M2 Pro provides a structured patient setup with anti-gravity support, an objective evaluation tool, the ability to perform group therapy with engaging and motivating activities, the ability to perform high-intensity therapy, and a cognitive therapy mode, which I think is really unique and really nice to see. I'm excited to see the application of this cognitive therapy mode in the clinical setting. All of these key features provide a platform that optimizes the opportunity for true arm recovery. However, as with any intervention, there are definitely limitations in neurorehabilitation robots that must be recognized. For some patients, recovery of the arm is simply not realistic, and for others, they do not respond to robotic therapy as expected. The mechanisms to explain this phenomenon are still unknown, unfortunately, and really do require further research and exploration within this field in order for robotics to be implemented and adopted in a wider scale. It must also be recognized that robotics shouldn't be considered a standalone tool. It should be incorporated with functional retraining tasks to optimize motor gains to real-life activities. Some of the more successful outcomes in robotic trials have been achieved when robotics is combined with functional task training. So this should definitely be part of the implementation and adoption plan for robotics when acquiring robotic devices in clinical settings. Nor should robots be treated like a recipe for each patient. Optimal therapy should be really carefully selected for the individual within these robotic platforms and based on the results of a detailed evaluation and, of course, the patient's goal. So we're not taking away the clinical reasoning that we spend so many years as clinicians building up and learning about. We're just using our clinical reasoning skills and adapting it essentially to the technology as a tool in order to optimize the patient's intensity of therapy and their needs in the platform that the robot offers. We're not taking away the thinking or the clinical reasoning that is so key in a clinical setting. For future work in this field, the objective nature of robotic evaluations leads itself to be very useful as a tool for determining prognosis, hopefully for the better treatment and discharge planning and optimization of a patient's rehabilitation journey. I think this is as a field, investigating biomarkers essentially for outcomes is really key in order to optimize patient outcomes and basically a better patient journey following stroke in rehabilitation. And although robotic therapy has been shown to be promising in many trials, the benefits definitely do not extend to all patients or at all stages of their recovery. So perhaps there is room to augment benefits of robotic therapy by combining with other interventions. What about virtual reality or transcranial magnetic stimulation, or even with EEG to create brain-computer interface platforms? And these technologies are perhaps still in their infancy and definitely combining with robotics, it's definitely a very interesting but unexplored and unvalidated part of our field, which I think has potential to be a solution for some of our patients. So let's go over what we've covered. Patients need and really want more arm recovery than what conventional therapy has been able to offer following stroke. Robotics provide measurement of and therapy for both arm recovery and really doesn't focus on compensation. Robotics offers an objective and sensitive tool for both evaluation and intervention and does facilitate more efficient therapy. It allows a high intensity of therapy to be provided in less time and can increase a patient's motivation, engagement, and satisfaction of their rehabilitation. Robotics can provide improved outcomes if performed in conjunction with functional retraining. And finally, that really individualized therapy is still directed by clinical reasoning, is still really key to successful patient outcomes.
So we have a first question coming from the floor. So I will direct this to you, Sarah. So what are the recommended frequency of robotic therapy?
Okay, thanks. So if you have any more questions, just type it in the Q&A box below and Jake will read it out and then I can try and answer on behalf of Taya. So I think I get this question a lot, and currently there are no optimal clinical indication. So there's no like set dosage or frequency for robotic therapy. So as Taya suggested, we definitely promote it and suggest to use it in conjunction with conventional treatments. So what we see is more feasible is to have maybe one session of 30 to 60 minutes of robotic therapy and then led by another session of conventional therapy. So what you focus on during the conventional therapy, it's the learning transfer of the robotic training to your functions, the day-to-day functions. Okay, so I hope that answers your question.
Okay, moving on to the second question. Assuming that rehabilitation robots are calibrated according to validated movement protocols to optimize recovery and safety for most of the patients, so what can we do as clinicians to further improve functional fit for patients who may not be the best served by the factory defaults? Should we learn more about kinematics so we can fine-tune the robot control algorithm within safe limits?
So that's a very kind of tough question. And I think as a lot of clinicians don't have the kinematics background, and that's why we sort of have to liaise with, the biomedical engineer. So Jake is actually a biomedical engineer. I'm a physiotherapist. So of course, if it's possible, I would say yes, but not all devices, robotics out there are actually able to do that, or you're able to kind of fine tune. So I would say as a clinician, it's better to actually prep your patients. So making sure they understand why they need to use robotics, why it's important for them, or prep them using manual therapy beforehand to then use the device.
Yeah, okay. I think me and Sarah, we personally feel this conversation actually a lot. So we always try to find, especially in rehab robotics manufacturer like us, we always try to achieve this balance between engineers and clinicians. And at most of the time, this balance is so hard to achieve. So even for a very basic things to be adjusted for an engineer, somehow it still feel like it is a tough thing to be adjusted or implemented by a clinician. So we hope that in the future, the robotics will be even easier to operate, easier to use, yet it can have the capability to tailor to every needs of individual patient.
Yeah.
Okay. All right. Moving on to the third question. So it is from Joanna. So thank you for the great lecture. If we should avoid compensation, but the ability to a real recovery is limited to 5 weeks. So after this time, it seems like there are no other mechanism for function improvement than compensation. So what is the neurophysiological background of improvement in the case of chronic patients?
So that really differs depending on which kind of, motor learning that you're concept. So I think there is a few different kinds. I can't really answer that per se in the case of chronic patients. And a lot of them, sorry, let me reread the question. There are no mechanisms for function improvement than compensation. So it's difficult because we obviously see that there is the compensation during therapy. And what we want to do with the motor learning is obviously just getting enough motivation and enough function for them to be able to do their day-to-day activities. Okay, so hoping that kind of answered that question. It's a bit of a tough one.
Yep. So what is the possibility of wearable robotics for everyday living? Just wondering about the transferability from rehab to discharge.
Okay. So there are definitely different kinds of robotics that we see with more and more wearable robotics becoming more readily available. And it really depends on what the patient wants to use that for. we see some robotics that are really just for rehab, and we see some that helps in the assistive living. Okay, so it really comes down to what the manufacturer has designed that robotic for. And also, however, with like robotics that are for assistive living, I wouldn't say, to use that all the time. It's to use that as a tool to be able to assist them. But it's definitely something that we can see it's more and more readily available for the community to use. And it's definitely a great tool if the patient is thinking about using that to improve their day-to-day function.
Well, me personally, how I understand this question, the picture suddenly come in my mind will be the lower limb exoskeleton. So when can we actually start to use lower limb exoskeleton and walk around like a normal person in a daily life? So it actually made me recall like more than a year ago during our grade submit. So our joint lab professor Danny Otomo actually gave us a sharing saying that there's actually still a big limitation in the mechanical engineering and in the motor, that it still cannot mimic like what actual human muscle does. So in a split second of time, generate enough force that can drive you to walk, drive you to run, etc. So this is the technical barrier that we need to break through at the moment. But personally, I still see a very positive. The way I see it is very positive. It probably it might seem very hard to achieve at the moment, but sometimes you are amazed and you are surprised how technology moves so fast in the past decades or past couple of years. So you look online and you see Boston Dynamics, how they develop the Spot, the little dog. It's just amazed how all the algorithm they have implemented inside, and then it's so smooth and so dog-like in that robot, and they are human-like robot. It's so impressive, like how the technology have developed in the past few decades. Yeah, well, we definitely was looking forward to see that happen in one day. People actually wearing lower limb exoskeleton, walking around.
Yeah, I think there is another question in regards to like using rehab robotics on their own as a home exercise program. So I think that's definitely we are definitely seeing that coming more and more, and especially with like the current pandemic situation, where lots of patients prefer to do it in the space of their own home. So I definitely see, there are robotics that are based for home. Will there be any safety features supporting the idea? So I think it again comes down to the manufacturer. But I think the key thing is to constantly have interactions with the clinicians, with the therapists that have given this the home exercise programs. And we're seeing tools such as, we have Teams, we have Zoom, we have the Microsoft Connect, etc., to actually really see the patient at home and do what we call the tele-rehabilitation. So I definitely see that there is a huge potential for this in the coming, sometimes even months and years, that we are going to see this becoming more and more common.
Okay, so we have another question from Benedictia. Is this suitable for PED patients? So I'm assuming it is from the M2 Pro devices from Taya sharing just now.
Yeah.
Is that suitable for PEDS patient?
Okay.
So I'll go ahead and answer that first. So it is actually not designed for PED patient. So because of the height of the devices is quite tall for a kid that maybe at 8-year-old, below 8-year-old. So we still recommend it to be an adult or adult height kind of a patient. And also when you started to use it on a patient, on a PED patient, you often find that their strength are far lesser than normal adult. So the force feedback mechanism might not work as well as like normal adult patient. So at the moment, it is not recommended for PED patient.
And I think I'll answer the one from Andrew, Jake. Yeah. So hi, Andrew. So Andrew is our really good partner in Australia. So this just reminded me. I wonder if the audience is aware that there is a method already in usage developed at Auckland University and other international collaborators to determine if a stroke patient has the ability to benefit from neurorehabilitation or not. So which is the PrEP 2. So I am going to show that and then so there is a link in the Q&A box. So the PrEP 2 really stands for Predict Recovery Potential, and it is a revised prediction tool for predicting the upper limb functional outcomes after stroke. So do have a look in the Q&A box below. And we probably have time for 2 more questions.
Yep, right. Related to the signal speed shortcoming in current gen lower limb robotics, is BCI research like what Taya is involved in the key to improving compensatory performance for robotic prostheses? Or what else could be the silver bullet for greatly improving wearable robotics?
So I think this one, so there are lots of other research and other kind of robotics interventions that is used in conjunction with robotics. So we see like, we have TMS, TDCS, brain computer interfaces, FES, things like that. And I think there isn't actually a gold standard for each of these different technologies yet. So I can't actually comment on what is the silver bullet for really improving the wearable robotics. And I think it just comes down to the more evidence that we have and the more kind of clinical studies to kind of prove the feasibility of these that would really strongly support what could be, better for our patients and the outcomes of that.
Another question would be, when you know the long-term viability of companies that develop and market new robotic systems or technologies, considering the high development costs and long market acceptance, will startups or established companies have the financial muscle to maintain their product offering in the long run? Do you know the current failure rate? Well, that is a very insightful question. Yeah, we definitely doesn't know the current failure rate, but I do see a lot of company, especially in Southeast Asia, where we are currently based in right now. Government has been heavily funded on all these technologies company, and we also see that in the recent stock market, technology companies has had their stock prices skyrocket. So there's definitely a future in the market, and there will be more and more people actually venture into this industry, and then there will be more support in terms of funding from the government as well to actually help the development of this industry. This is also what we are very looking forward for this, and we're also very looking forward for the outcome of it, like what kind of technology that can really come out from this talented inventor and these companies, and how they can benefit the human being. So yeah, we see how Iron Man in the movies or those robotics in the movie, somehow it's for sci-fi fans like me, I really hope that someday it will happen. We open the window and we see flying cars.
I think just to kind of add on for Jake, though, we definitely see that the industry is booming. So a few years ago, you have, a few numbers of companies that are developing exoskeletons, but I think currently we have over 100 companies that are actually developing like rehabilitation exoskeletons. So there is definitely a lot more competition in the market nowadays. So for anybody who, whoever that asked the question, I want to start the startup, I'd say, definitely think about the technologies really. I think it's the core technology that will help you maintain the product offerings in the long run, and think about the patients and the clinical implications of that.
Thank you guys for joining. Thank you for your time. So if there's any further question for the session today, feel free to send us email to contact us through clinical@fftai.com. So thank you for your time today. We hope you enjoyed it.